My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Good evening to all. So hope you are well and safe from Corona pandemic. So as we know that we are staying in a Corona pandemic situation and situation becoming very worse. So we have to follow our health rules. So it's very difficult for us to continue our normal academic program inside the campus. So we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. We have successfully completed our 213th international physics webinar, including 3 Nobel Laureate speaker, and today it's our 214th international physics webinar. And we have with us here today Dr. Jashamant Narayan Mohapatra sir, Professor Department of Physics, Indian Institute of Technology, IIT Kanpur, India, and he has already connected with us. So I'd like to welcome our speaker, sir. Good evening, and thanks for accepting our invitation, sir. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. So before going to you, I'd like to introduce you with our student and the viewers. So they are student and viewers. I think you have already come to know the title of the today's International Physics Webinar, and the title is Visible Electronics, a Revolution in the Making. Very interesting and exciting topics. I think you will enjoy it. And our speaker is Dr. Jashamant Narayan Mohapatra sir, Professor Department of Physics, Indian Institute of Technology, IIT Kanpur, India. And we can see Dr. Y.N. Mohapatra sir completed his bachelor 5-year integrated MSc from BITS Pilani 1981 and PhD from IISc Bangalore in 1988. And now he currently working as a professor of the Department of Physics, IIT Kanpur. And we can see his research gauge ID, and his research gauge point is 35.68, and his Google Scholar citation number is more than 1300. So thanks for your patience. I think you will enjoy our session. So sir, I'd like to welcome you again. Sir, it's your time, sir. You can start your session, sir.
Okay, so first, it's a pleasure to be talking to. Yeah, it's a pleasure to be. Thanks for contacting me. So this is one of the advantages of pandemic.
Yes.
Since we cannot travel, but we can still really collaborate. Yeah, right.
Yeah.
So how many minutes is it going to be?
So you can talk about 1 hour.
Okay, all right. I will not take that much long, but I'll see the. All right. Okay, so of course I have never been to Bangladesh, but it's very much.
I will definitely invite you.
Yeah,
after
sure.
the COVID.
Yeah, sure. Now I am going to share the screen, right?
Yeah,
just a minute.
Maybe you have stop share.
No, I did not. Okay, let me see. Share.
Yeah, now.
I'm there, right?
Yes.
Yes.
Now click.
So,
yeah.
Yeah.
And just click over hide, that hide option. Just please.
Yeah. No. Now you can see me, right?
Yeah. I can see.
You can see my
just
slide,
click
right?
over hide. Yes. Just not stop share. Hide. Yeah.
Hide. Wow.
No. Yeah.
Okay.
Yeah. Okay. Now okay.
Now you can see. All right. Okay.
Yes,
so good. So let me tell you a little bit of before I introduce. I am, of course, as you said, Jashavanto in Bengali and Yashwant in North India. Okay, most of the time, while Mohapatra. I am associated with physics, material science program, and Samtil Center for Display Technologies, and now also we have a new center called National Center for Flexible Electronics. This is a center in India which coordinates all the activities in flexible electronics in the country. Okay, and I will be speaking from that perspective. Now, my today's talk. Okay, let me tell you what I work on normally. What I work on is the problems of electrical engineering which physicists can solve. All right. So not 30 minutes, you give me 1 hour, but I'll extend it, okay, to 1 hour. I thought it's initially for 30 minutes. All right. Okay. So, initially I was to be a hardcore semiconductor, like silicon and gallium arsenide and things like that. Right. And so sometime back, or almost 2 decades back, we switched to focus on flexible electronics. And that is what I'm going to talk about. I'll give you a little bit of introduction to our center also. So I'll tell you about why it's flexible is required, what are the kind of worldwide efforts going on, and I'll give you a little primer of technology development and the role of physics. I'll take one or two examples in telling you how can physics community can contribute to this huge revolution that is passing through us currently. And we have, I'll talk about materials, inks, and substrates, examples of fundamental problems, and I'll end with a little bit of example of large area printing and what are the current challenges. I will not go deep into any of these subjects, but because it will be introductory, but I'll try to give you a flavor of the subject. All right. Okay. So let me give you a history of how I started. Around 2000, we formed a center in IIT Kanpur, which is on basically focus on organic electronics at that time. Okay, so main idea is to have a co-development with industry. Okay, so academia, government, and industry. So we don't take any funds from the institution. We always try to generate and get industry interested in problems such that the government can give us some money to do this tripartite. So that is the idea. Around 2005, for example, our center already had capabilities that we could make a passive matrix display meeting industry standards at the center, okay, along with an industrial partner. Okay, so this is around 2007, I took up a major program on printable electronics. Okay, so that is shifting from organic electronics to electronics that can be printed. I'll be talking more about it. Okay, and around 2010 or so, we started many other technology programs, not just display, but organic photovoltaics, lighting, sensors, and so on and so forth. And in 2014, that is almost 6-7 years back, we started a completely new center to be able to generate a lot more industrial problems. So we have this center in which we do research, and we have also this center in which we take up a lot more industrial problems. And there are people, as I will tell you, that from all branches of discipline working at the center. Okay, this is the National Center for Flexible Electronics. Let me just switch off the lights. I don't require any more. All right. So I think there'll be opportunity for some of you to visit us. Okay, and so I'm trying to invite you. Now, what is for a physicist? Okay, let me bring it down to what is a technology platform. Okay, a technology platform is for this particular flexible electronics. This is printing of circuits on flexible substrates. That's really the area. Okay, just like you have, let's say, newspaper being printed. Can we print electronics on flexible substrates like cloth, paper, anything? So you don't have to be rigid like in silicon. All right. So what do we need? We need some photovoltaics and battery on it. Okay. Some sensors like temperature, gas, pressure, electronics, which would mean thin film transistors, memory, diodes, and passive like resistor. Okay. And let's say actuators like light emitting diodes, displays, speakers, everything we should be able to do on plastic or paper. So system, so we call it our approach as system on plastic or paper or SOP. All right. So at the center, we have programs on. I'll give you just briefly the kind of program that we do before I come to the actual topic. So we have a huge project on thin film transistors, organic LEDs, organic photovoltaics, sensors, producing functional inks. I'll tell you what functional inks mean, and printed batteries. Okay, we have not developed printed batteries so much, but there are a lot of effort in the country. And then once you have these elements, then you can do technology integration to produce many applications. Okay, like memory and logic circuits, solar modules. We have many products based around anti-counterfeiting. In fact, this is one of the major industry partners. Okay, healthcare devices, and of course displays, and what we call as smart packaging. So these 6 areas are our main focus in terms of application, and these 6 areas are the areas in which we actually develop the technology such that some of these applications can be done. Okay, so so that is what our center is all about. All right, so I'm not going into the administrative aspects, but let me come to, we all know as students about diodes and transistors. Okay, I call diode as the wheel of electronic civilization. It has two, instead of two wheels, it has two legs, right? But electronic civilization really started with a diode when you could control something, right? So it is not just a resistor, but, and then from there we went to the tricycle, transistors. Okay, so this is the brain behind electronics. And from diodes and transistors we went to actually ICs. Okay, and so electronics needs both. Okay, and electronics is successful because it integrates extremely large scale, as you can see in the middle. Okay, all elements, whether it's transistors, let's say in your mobile at the moment, how many transistors do you have in the CPU? Okay, probably a billion. In that little 100 micron by 100 micron chip, you would have billions of transistors working in unison. Okay, so that is all electronics, and electronics is really about integration in large scale. It is not about just one single device. Okay, so let me ask you a question. You see, this is can you see that is diamond? Okay, and then these are of course flowers and greenery, and this is graphite. What do you think is common to all these? Okay, I don't know, I'm not seeing the chat, but you can tell me what is common to all this. Okay, all this common is actually carbon. Okay, so you have sp3 carbon gives you diamond, and you probably have learned about diamond structure. And you also know probably of the C60. Okay, the and carbon nanotube, you must have all heard about. So you can see there is a huge, carbon gives you a huge variety. Also, this is sp2 bonding can give you graphite. So these different kinds of bonding of carbon can give you a whole areas, inorganic, organic, and even soft electronics that we are doing at the moment. All right. So you can see in the periodic table, the electronics revolution so far has been based on this fourth group element, silicon. All right, and now the same group C is also in the same group. So slowly the effort is shifting from silicon to newer applications areas of carbon. Okay, in many different forms, and that is what. So the new electronics is probably going to be the question between carbon and silicon, not or silicon. There will be carbon and silicon, but there will be a lot more uses of carbon, as you will see. Okay, so this is a science that is this area, the whole area is a science-induced technology. Okay, and as always, it is started with lots. If, for example, you could see this, the chemistry Nobel Prize in 2000 went to Higa, Alan Higa, McDermott, and Hideki Shirakawa for, you know what, for inventing the fact that plastics can also be made conducting. Okay, so making plastic conducting. Okay, in fact, McDermott was visiting Shirakawa's lab when he saw some, Shirakawa had made some polymer and that was shiny, and from there he got attracted. Why is it shiny? And then he figured out as that it was indeed a metal. And Heger did the experiments, McDermott did the theory, and they got the Nobel Prize for that. In the same year, we had the Nobel Prize for heterostructures. Okay, I don't know if you can recognize this man who was given Nobel Prize, Jack Kilby, for IC, and this is Herbert Kromer, and this for heterostructures. That is two different materials. Okay, instead of silicon, if you can have silicon and gallium arsenide, or gallium arsenide and something else, then the applications can be a lot more. And these two ideas were taken by, pioneered by two different ways, okay, to produce OLED, okay, small molecule, and Richard Friend for polymer in 1990. So these are small molecules and polymer. So these ideas of making plastic conducting and heterostructure were both taken to for organic molecules and used for to make devices. That is, and this was about 1990 and 1986. Of course, this work was done much earlier. Okay, and so this was the starting point for this discipline, and that is why. So in organic electronics, let me, instead of flexible electronics per se, you could make an LED. Of course, that you have seen LEDs now everywhere, lighting, white lights, or solar cell. We can make solar cells just as you make in silicon. We can make transistors on paper just as, but of course their capabilities and functions are different. We can make sensors. So organic electronics tries to produce. There is one difference though. This is all we call is microelectronics. Okay, based on silicon. Okay, all these are based on carbon or organics, organic molecules. So, and this is over a large area, and it is macroelectronics. So this is a technology which is motivated by electronics for everywhere, for everybody. Okay, not in a box. It should be in a large area. All right. So these are typical components of flexible electronics. What are they? You have an organic light emitting diode. Okay, for example, a glass substrate has certain layers of organics, and then is a cathode and anode, and it can produce a light. It can electroluminescence. That is a basic. Actually, that the discipline started with development of organic light emitting diode. Okay, and then we have organic thin film transistor. We have source, drain, and in between a semiconductor which can be produced in a substrate which is either a paper or a and have a gate and a dielectric. So complete transistor. So it's called organic thin film transistor. You can have a solar cell. You can have a memory. Okay, and it is extremely cheap to produce them because it's on paper and with wet methods. Okay, in the lab, it doesn't require a billion-dollar industry to produce them, and hence so it is cheap, it is large area, and it is wet chemistry. All right, so these are the typical components of flexible electronics. And what have they have a role in grand challenge in energy, in health, in environment, in education. Okay, so for example, these are some of the internationally developed. I will show you ours also. This is flexible displays by Fujitsu, flexible organic photovoltaics developed at Fraunhofer, for example. I'm giving example, flexible battery, and then a robotic skin. Okay, a robot can have many transistors to make either feel pressure or light or chemical. Of course, it is already in packaging tags. It can tell you the freshness, and it's a smart tags in food items, and almost like computers in poly IC. I'm giving you just, so it's a new age of what you can call as macro electronics. Okay, similar, it is displays, thin film electronics, solar cells, lighting, radio frequency, ID. In fact, this is one of the areas in which that's taken the maximum, and of course sensors. The difference between microelectronics is should be now printable, just like you print newspaper. It should be flexible. It should be large, not small, and hence is macro. In fact, some people call it as meter electronics. That is, this is electronics that you produce in meters, and is disposable. Maybe in future you can take a TV for your picnic, and it has a life only for the picnic, and at the end of it you dispose it in a garbage box, and you use that TV outside and dispose it. So it's disposable and it is cost effective. So this is not supposed to replace any of the existing electronics, but is supposed to increase the application areas of electronics and with these characteristics. All right. So how do you do make? You can make small molecules in a high vacuum deposition. This is from our lab, which doesn't have much bigger advantage for example, for organic electronics. But yes, you can do that. In fact, normally we do research by producing these in a sophisticated molecular beam epitaxy like system here. Okay, but what is more important is making things like on a transparent substrate having multiple layers, which is just produced from solution. For example, I'm saying here that I put quantum dots, okay, which are inorganic into organic, okay, and then coat them to produce, for example, cadmium selenide. Okay, this only. So you are doing large scale devices, but you are including functionalities which are at nanoscale. Okay, in fact, for nanotechnology, this is probably the first uses. Okay, that you tailor the property of the device by including quantum dots which are inorganic into an organic matrix. All right, and then we can make a text device. For example, there are 4 LEDs one of my students had made, where it says, and the light comes out from cadmium selenide. Okay, and the organic and this, you can see that as if they're embedded in a polymer like that. And what is the advantage of doing that? Now you can actually spread over a large area with a very simple technique, with simple techniques. You don't have to require a molecular beam epitaxy like vacuum system. All right, so that is the advantage that I wanted to show you. So it is really nano engineering. You are engineering at the nano level, but really not one by one. Okay, for macro electronics, for large area electronics. Okay, and you get advantages by either packing molecules, okay, or blending them, or embedding like C60s, modification of C60s or carbon nanotubes into. And why do you do that? For better luminescence, okay, for better mobility of the charge carriers in the substance, for stability of the material, and what we call is not electronics, really excitonics. Okay, I'll tell you about excitons as we go along. The key use of in this area is nano ink development for flexible substrates. I told you that we need to print. We need to print, but you need metals. Okay, and metals, you can, for example, gold or silver. Gold melts at thousands of degrees Celsius, but I'll still need it on my paper. How do I do it? Okay, and then I require semiconductors which are polymer or small molecule, and they should be soluble. Okay, such that I can make. So I can make soluble CNT and so on and so forth. So we have a way to make it small, but functionalize it as chemists do it. They put molecules on, let's say gold, such that they can be made soluble and can be processed at a very low temperature on my flexible substrate. Okay, to give an example, this melting point of gold is 1064 degrees Celsius. Okay, but if you make the gold nanoparticle, which is only 1 to nanometer, the melting point or at which we deal with can come down to 153 degrees Celsius. All right, so now meaning there are molecules attached to it at 153 degrees Celsius heating, and plastic substrates can take that. In fact, we have gone down to 145, okay, degrees Celsius. So how does one do it? For example, you can see these are gold atoms. Attached to it are those molecules. If I don't attach these molecules, this is not stable. Okay, because the surface area is a lot more active, and hence they will just form gold, and you cannot make. So but chemists are clever people. They can attach things which make it different. And now I provide heat or energy by which at the right time it can go off. This sort of, if I provide a little bit of heat, then it's only the bonding between this organic molecule and the gold, okay, that gets energy, and now it goes off and then forms like that. And so we have done all these studies, and finally forms out of these three, you will form something like that, okay. And that, for this to happen, it only requires 153 degrees Celsius, okay, not 1000 degree to melt. And hence I can coat gold wherever I want on my flexible substrate. I'm giving an example of nano engineering required for this macroelectronics. All right. For example, we have also made some conductive silver pen. Okay. This is now becoming an. I'm starting one of my students is doing a company now, which can now sell this flexible conductive pen, silver. It is put in silver, and you can draw circuits. So this is a circuit which is drawn with silver, just like a pen. Use the pen, and but it is packed like that, and I can control the resistance by the length. Okay, and you can see some of the applications here. We are making a whole laboratory kit so that it can be given to the school for making circuits and easily integrating LEDs and things like into that. And you don't require wire, you can simply draw it. Okay, so this is like a draw a circuit, and if you now put the switch on, and LED comes on. So we are using it for cards and for many of these. So this is by converting silver into ink pen. Okay, so that's we have an Indian patent and a company coming up. Here, let's say we have painted, we have conductive ink on textile on a large area. Okay, so in-house we have printed, and this is such a large. Okay, this is a huge corridor. You can see this is printed silver, and it is only 1.2 ohms per square. Okay, so this is printed over by a printing method. Okay, so what are these uses? From these you can make some things in which you can keep your passport, so that nobody can steal, or even cards. Okay, such that it can be shielded from electronic theft. Okay, so most of your purses would become like that. So we do silver screen. You have copper. Now one of the major programs, silver is expensive. Can we replace silver by copper? So we are doing that copper, and we have for different methods, for different inks, for different kinds of. We can do inkjet printing. Okay, just like you print your papers, we can do inkjet printing of circuits. I'll show you that. Okay, so we can do polymer and all kinds of inks, and this is one of the main characteristics of flexible electronics. That is functionality. In normal printing, you have color, red, blue, green, and so on and so forth, right? Or magenta, cyan, and yellow. But here we require dielectric, we require metal conductor, we require semiconductor, and so on and so forth. And that is what so you print, but you print functionality, not color. All right. So that is what we do for making different. Okay. So this is a conductive cloth, for example. You can see that this is a cloth which is fully conducting. So if I now touch in any part, it makes it glow. Okay. So these are full parts made in our lab, for example. All right. This is only 1.2. This is just a demonstration. Okay, so it can be used for card protection or information protection. Now let me quickly go to some more devices. Okay, for organic light emitting diode, it is now becoming, of course, now there are your mobiles have all organic light emitting diode, but that's very expensive for devices. So at the moment, let me give you a simple principle of the organic light emitting diode, because there is a cathode and anode on a substrate. Substrate could be paper. We have a paper LEDs also, or more like a glass or a cloth anode. And there are several layers of organic layers. Okay, you simply coat them with a inexpensive method. Physics-wise, what it does do is, if you now inject a hole through anode and electron through the cathode, then they recombine and so this is like a conduction band. It is the lowest unoccupied molecular orbital and highest occupied molecular orbital. These molecules are pi conjugated molecules, and hence this is only 2 point only, difference is invisible. All right. So, and if you now inject electrons and holes, they can recombine to give you light. Okay. And since if you take a transparent substrate, then the light can come through. You're probably familiar with it. This electroluminescence, except that this combination of electron and hole is slightly different from that happens in a normal LED, because this what they form is an exciton, because of the Coulomb attraction is much larger, so they immediately form an exciton, and you get excitonic recombination to get this light. All right. I do not know if you're familiar with this. Okay. For example, we make this OLED in a cluster tool, which is the robotic control, the central control. We have three colors for three robots making three different colors, and we insert, for example, here you can see you can insert the glass substrate, and it gets coated by red, blue, and orange, and gets packed and comes out. Okay. So some of my colleagues who do that. So this is, of course, for an industrial project. The lighting panels. We can make lighting panels now. Doing that, the application area is you can make it in an office architecturally, all right, or architectural panels. Okay, some of the uses that I can see. We have also made flexible solution processed OLED. Okay, and we're looking at a pretty good performance. You can see that the current versus voltage is like a normal diode. All right. So the idea is the kind of, for example, here it is a tulip festival in Japan. So we are making these such that they can be used in applications like that. I'm giving a very quick example of what it can do. For inexpensive scooters and mobiles, you can even use it, replace it with colorful displays. Okay. So this is a printed 7-segment display. It's not what you can buy in the market. This is actually printed. So you can make it as large or whatever you can do. This is made in our center. All right. We have a dot matrix printer also. Dot matrix display using these LEDs. All right. So you can see that this the full electronics is being done in our lab. Okay. So if I do that, so you can, and it can be made as large as possible. This is just as a demonstrator for industry. All right. So Signages, we have now joint projects with industry such that it can be made with Signages for tail lights and automobile rears and all that. Okay. In fact, long back, it's almost 10 years back that we made a flexible passive matrix OLED display, full-fledged display. Okay. But of course, it is passive matrix. At the moment, what we use in your mobiles is active matrix. All right. Such that you can have applications like that. Okay. We are looking for industrial partners which can make it flexible. And so this is a Samsung display is trying to produce that. All right. Now let me give you a physics example. I've given you a sort of application areas. I'll come to more as time permits. Okay. So let me give you at least one example of physics example. Okay. So let's take a glass substrate and put these. You don't have to be familiar. There's some organic molecule. Okay. But these molecules have one characteristic you'll see in common. That is, there are alternating bonds for double bond. Sorry. Okay. Let me go back. Okay. Alternating double bond, single bond, double bond, single bond. Okay. So these are the kinds. So what does this alternating single bond and double bond do? That is, this pi electron, which is a double bond, loses its address. So it becomes, it can travel all through the molecule. Okay. So it becomes delocalized. And that there is the physics there. Because it is delocalized, okay, the energy required to make it electronically exciting is much less. And that is why these compounds, and here, of course, this is used for doping. All right. So what we did, for example, Here, instead of making a proper diode, this is a glass substrate, and then on that we have indium tin oxide anode and several layers, and in between we have a high low doped undoped junction is only a few nanometers, 150. In fact, we change this in between layer by from 10 to 100 nanometers in our experiment. All right, so we form a diode not by PN junction, okay, not by silicon, P silicon and N silicon, simply by coating, wet coating of organic layers. All right, and then you can see the IV characteristics. I'm sure you are familiar with IV characteristic of normal diode, but you can see beautiful diodes can be obtained where the current density can change from 10 to the power minus 9 to 10 to the power minus to 7 orders of magnitude, and you can see the reverse current is so low. Okay, but what is interesting this is this: the physics of this IV is very different from what you have studied in your text about PN junction. Okay, why? Because there is no real electrons and holes being here. This is an excitonic. All right, so you can see that we have studied this as a function of temperature. This slope is independent of temperature, whereas a normal electronic diode, you would get this as a function of kBt, but here it is independent of temperature. All right, so these are different temperature, 175K to 300K, this forward rise of current. All right, I don't know if anybody is asking any question or not, but I can't see the format. I am more familiar with the Zoom. Okay, I can't see any chat while I'm doing this.
Yes,
Uh,
I can add.
but
We have a question. I can add the question if you,
yeah, yeah.
or we
If
can
I
discuss later.
Yeah, sure. All right. But let me go ahead, okay, and tell me when time is there. I don't know. Okay. So this is, for example, the current, as I said, you is proportional to exponential of V with a temperature independent slope. That's what. Okay. This is a long time work, but I thought it will be understandable by you, so I took up this example. This temperature independent, this exponential slope. Okay, so what would be the physics is very different. I'm trying to tell you that you can get a diode, but the physics of diode, of an organic diode, is very different from the physics of normal diode. That's the point that I'm trying to make. Okay, so we showed that this is really because of tunneling. I'm sure you are, as physics students, you are familiar with tunneling. So this is at the interface. The density of states can be changed by the voltage, and if I do that, then it could be actually be tunneling from one density of states from one layer to another layer. And since it's tunneling, it is independent of temperature. That is the if you don't understand all the details, that is the thing. That is a threshold voltage beyond which I'm aligning the unoccupied density of states with the occupied density of states, and because of that there is tunneling, and that is why it is, and hence a physicist's involvement is required to understand even basic phenomena in some of these new technological developments. Okay, I just wanted to give you that example. So this current is very different. In fact, we can obtain this Gaussian distribution of density of states from this. It's all right if you don't understand fully, but that was the achievement that we said, that simply on the basis of IV characteristics as a function of temperature, we could measure this Gaussian density of states. I don't know if you have done solid state physics or not. In solid state physics, you have a three-dimensional semiconductor. The density of states is e to the power half. It's parabolic. Okay, but in organic semiconductors, since this is not a crystal, this is a completely amorphous. We have a Gaussian density of states, and there are many ways of measuring Gaussian density of states. But here is a simplified way, or you can measure what is the density of states of, and you can explain the phenomena. Okay, so you can measure that. Let me take another example of printing electronics on paper, plastic, and cloths. All right. So in our center, of course, we started around 2015 or so in printability, and now we have full roll-to-roll processing. Okay, I'll show you example of that. So this is a technology roadmap for us. and we are somewhere already there. All right. So in our center, we have all kinds of printers. Okay, just like so you have inkjet printing, for example, Pixel Draw. You can inkjet large area inkjet printing. We have small inkjet printing with the Fuji diametrics also. We have screen printers of different kinds. Okay, we have yeah, I'll show you, Dr. Blade, wear bar. So because different applications require different kind of printing, no one type of printer will solve one type of application. Okay, in fact, some of the applications might require three different kind of printing. Okay, and hence what we have done is we have collected all kinds of printing techniques and developed a whole printing laboratory. Okay, for example, large area inkjet printing. Okay, if there are 512 nozzles here, then in a single pass you can make, so that is about 10 millimeter. Okay, then we have 2 into 10 to about 1000 nozzles of for roll to roll printing with Pix Draw. So we can have multiple to make a full A4 size printing at a very high speed. All right. So this is one of our let's say this is a full-fledged industrial printer. It is according to our design, but made in UK, and then reinstalled here. Of course, the contribution of different parts have come from all over Europe. So this can print. So this is of 0 to 10 meters per minute, or even 50 meters per minute. So this is almost like newspaper printing or magazine printing. Okay, for 10 centimeter to 30 centimeter wide, you can print. All right. And so there are two printing stations. So one method could be here. You could be doing inkjet printing here. It could be doing screen printing here, or you could be making two inkjet printing. I'll show you example. For example, this is is almost like 20 meters. Okay, configurable 20 meters, and you can interchange printers. Okay, so there are different printers you can simply interchange inside my clean room at my center. There are different views of the same. This R2R meaning roll to roll printer line. All right. So let's take an example. This is I'm printing. I've taken a flexible plastic. All right, and I'm printing a heater for jacket, for heating a jacket. All right. So I take print substrate here and then load it here, and then it unwinds the substrate. Then I clean it with plasma. Okay. And then I print one coat, something like this, one coat of silver. Okay, so there are one coat, and then I dry it or sinter it. You have to dry it or sinter it to make sure that they become silver. All right, so drying and sintering, and then we print another coat. Okay, in which I print the actual resistor. Here I printed the conductor. I printed the resistor like that. Okay, and then again I dry and coat it. So the length depends upon this drying. It is dry air. All right, but there are different. I can do laser drying also. So all these methods are there. All right, and finally you can do lamination and rewinding, and so this is roll to roll. So you can make heaters which are like large size heaters to be used in courts. Okay, for warmth. All right, and so we have that product also. So I'll give you an example of printing roll to roll technology. So I give you a physics example. I gave you a full-fledged industrial example of industrial printing. But the logic of electronics is really thin film transistor, and so we also are doing fully inkjet printed organic thin film transistor. Okay, this is a large size. There are 6 printed transistors, for example, on this. Okay, of course, this is continuing. I will not show you any further because they're being done with industry. We have a whole project on organic solar cells. Okay. This was Higa in 2007. He thought inks with electronic functionality. That was his aim, and that is what now we have. This was his dream in 2007, that you can actually print such that you can have solar cells coming out, not like big that you have seen on top of roofs, but which can be wound like that. And that is really now there. You can print solar cells like a printer. All right. So we are there. So I'll show you a physics example quickly. JV characteristics again of a P3HT PCBM. This is a basic Okay, so ITO, P3H2, PCPM. So you can see this is the diode without light on. Okay, and as soon as I put light, okay, then this reverse characteristics, for example, jumps from 10 to the power minus 7 to 10 to the power minus 3. Okay, and that is a organic photovoltaic device. Okay, this is of course not meant to be for efficient, but for efficiency, of course, you have to work harder. But I'll tell you a little bit of physics about it. So this current is like a normal diode current. Okay, you would expect. Okay, and so we make open circuit voltage measurement. Okay, to be able to figure out the physics inside it. So what is open circuit voltage? You put light on but don't draw any current, and then open circuit, and then suddenly close it. Okay, then you can see how it decays, and that tells you how the electrons and holes that you have created are recombining. Okay, but notice the time scale. This is almost from nanoseconds to hundreds of seconds. All right, so other people had done this, but they had not done the right experiment, and hence their conclusion was different. This student figured out how to do it right. You can see that it is logarithmically going down almost like a straight line over nanoseconds to hundreds of seconds and minutes. Okay, or in fact hours. Okay, so the physics is different, and it would have happened in microsecond in a normal solar cell. Okay, so and we worked that out. We studied that as a function of temperature. Okay, this is the voltage, open circuit voltage in from nanoseconds to 10 seconds. This is a huge amount of data. Okay, obtained at very fine scale. I hope you can imagine what amount of data has been done to be able to figure this out. Okay, as decrease, and this is linear. That's the first thing we figured out, and there is small dependence on temperature, and so we figured that out. Okay, so and then from there we figured out the dynamics. I'm not going through the dynamics here. Okay, let me come towards the end of this lecture. That is, I'm trying to tell you that in this area, technology is moving very fast, but there is science has to be there. Otherwise, you cannot do this technology. And hence, physicists have a role in playing and understanding the phenomena in these devices. But what is this area? The Herbert Kromer that I said got a Nobel Prize for heterostructures. I call it the Kromer's Theorem 1 in Nobel lecture. The principal applications of any sufficiently new and innovative technology always have been and will continue to be applications created by that technology. So it is new technology that is important. Okay, for example, new kind of sensors, new kind of technologies that is important. It is not to replace what silicon or gallium arsenide has already done. Okay, so and that is why there is so much of activity to produce what is it that this technology can do and solve. Okay, the Kromer's theorem 2, I said, ultimately progress in applications is not deterministic but opportunistic. Okay, that is, you just because you have these devices, the fact that it will be applied to some device is not. Okay, so it's some industry or somebody has to make an opportunistic, okay, use of these, exploiting for new applications. Okay, so that is what is important in this area, and that is why it is still a developing area. Okay, that you can bring through your anybody can say, oh, maybe I can solve this little problem, even day-to-day problem, with this flexible technology. Okay, in fact, we hold competitions to figure out new ideas. So this whole area is brimming with possibilities, okay, in applications and achieving them. So this is an invitation for you to join this challenge. Now, let me end with telling you in this area what are the 4 challenges, okay, that in making electronics flexible. Okay, there are 4 major challenges from which all our problems come from. Okay, so the challenge 1 is all low temperature processing. For example, I told you the substrate is paper, plastic, or textile. Okay, and hence every processing for a whole device has to be done at very low temperature. Okay, otherwise paper substrate or plastic or textile cannot take it. So for example, I told you that developing functional inks, print and sinter, everything has to be done in less than 150 degrees Celsius. Okay, or you have some people are trying with high temperature substrates like steel. Okay, or flexible glasses. Corning willow glass now is available, but it's very difficult to handle. We are trying that. Okay, but can I make a roof made out of very flexible steel? On one side I have solar cells for energy, and on the other side I have OLED for lighting. Okay, so in the jungles of Sundarban, I can have rooftops with steel, with photovoltaic on one side, and organic light emitting diode on the other side. Those are the kind of challenges that this area has. Challenge two is you have to be it has to be bendable. You have to wear it, or it can be stretched. It should be able to stretch, and hence mechanical engineers are in this area to make it both electronic and mechanical. So change properties and life of the device with bendability and stretchability. Okay, it should be wearable. Maybe it's in my t-shirt. Okay, the electronics is in my t-shirt, so I can put into my along with the electronics, which has OLEDs and transistors. I should be able to, most sports people for example, monitor their content of the sweat, from which they can figure out what they are doing at one particular time. So those are in the fiber or threads of the jacket they're wearing. So that should be wearable and washable. That is another challenge. All right. Challenge three is, since everything is being made at a low temperature, this also measure the life is small. And why? Because oxygen or moisture can get into the device, and that can degrade the device. So one of the major challenge is, how do I, at a very effective cost, encapsulate the devices that I make? Okay, that's encapsulation and degradation, because oxygen is the enemy of most of these devices, and oxygen can go through many of these, or even water. All right, so we measure how much of water can go through some of these things inside per in a day. How many micrograms per day can go into this? So sealing is a very, or self-healing also. Okay, sometimes it should be able to help. Suppose there's a tear, it should be able to heal itself. Okay, so this is a major challenge in this area. Okay, and of course it has to be a large area, and it has to be cost effective. So that is high throughput. It is not in microelectronics you get millions of transistors in one few inches. Okay, here there will be miles of electronics, and this will become cost effective only when you can do it high throughput. Okay, that is 50 meters per minute or 100 meters per minute, and hence it has to be roll to roll processing, and hence the application should require devices which will be used in millions, so that in a day, in a month, you can produce millions through a roll to roll processing. Otherwise it will not be cheap. All right, so these are the four conditions required for successful use of this technology in this area. In printed electronics, is currently you can always see that research resources, printed electronics being researched for last couple of decades. So the research resources are decreasing. We are somewhere here where the product development is really taking off for commercialization. Commercialization fully has not really happened. So we are somewhere here. So there is a lot more emphasis. For example, that is why I moved from Central Center for Display Technologies, where I used to do more research, to a National Center for Flexible, where there will be more industrial research. So this is where the product development is there at the moment. So that more, if you don't do this, this is going from research to commercialization is called the valley of death. Most of the efforts actually you fall, okay, and you die because you don't reach commercialization. So this is currently is in this phase. Okay, so that, and then soon probably once this succeeds, it will be everywhere. Okay, there would be all your walls, tables will be all filled with flexible electronics. So this is one of the products, for example, that is everybody in this area says finally, okay, that you are almost carrying a pen, and then when you, sorry, let me go back to that. That is like a pen, but and you want to take it out, then it's like a computer. Okay, so that would be the kind of the products that we are really looking for. All right, so I have just it gave me an 1 hour. I have 5 minutes for questions or so. So I'll acknowledge my team, Flexi team, and my students, and of course my funders. The Government of India and the Ministry of Information and Technology. Okay. With that, let me hand back to you for questions. I have not seen any questions uh, during the this thing, but I
So
can
thank you,
now.
sir.
Yeah,
Yeah, you can see the question section,
yeah. Oh, let
comment
me see
section.
how do I comments? Yeah. Oh, yeah. All right. So
So
I
the
can
first
see now.
question, yeah, what are the high energy electron mobility transistors, and how they can be used in flexible electronics?
Uh,
Can you see the
uh,
question?
you are
Okay, I
reading
can
from.
add the question. Yeah, the
No, no,
first
just
one.
a minute. I can see that physics are the astrophysics, astronomy. No, which is the first question? I don't see that.
Yeah, I can add the question in the screen. Please
Yeah. Okay.
check in the
Right.
screen.
Okay. What are high electron mobility transistors and how they can be used in flexible? Okay. Typically, high electron mobility transistors is typically in silicon germanium, okay, or gallium arsenide. So their mobility can be here. It is high electron. If it is 1 centimeter square per volt second, even that is high. At the moment, we are working for 30 centimeters square per volt second. Okay, that would be high in this area. All right, for applications. So it is not like silicon germanium where you have extremely high for fast. No, it's not for that. So the aim is to get both electron mobility and hole mobility of the order of only 30 centimeters per volt second. At the moment, we get 6 centimeters per volt second, and that is good enough for most of the applications on flexible electronics. Okay, this is not to compete with silicon germanium, for example. All right. Yeah. Next question.
Okay, sir. Yeah, thank you, sir. We have another question. So, what role graphenes can play in flexible
They are playing a big
electronics?
role. I am also getting into. We can print graphene. Graphene is a good conductor and transparent. All right, and hence graphene inks. It's have been made. We are also making, but we have not made as much progress as some other people, other countries have made. And already transparent graphene is being used in OLEDs. Okay, but they're still expensive. Okay, to print.
Okay.
Graphene itself is not expensive, but they're expensive to print. But yes, graphene as a conductor is going to be used in flexible electronics in a big way, in thin film transistors also. Okay.
Okay, sir. Thank you. This may be the last question. So, is the gravitational attraction may be called one type of nuclear interaction? I think this may be the not related to this exactly this
No,
theory.
yeah. So that is yeah, right.
Okay, so
Uh,
there is another question in inbox. I think you can't see it, so it's a message. So can I read? So what
yeah,
is the
sure.
value update?
What is the?
Value update.
I can't see the question. What is the?
Okay, I can send in the chat, private chat.
Yeah, yeah.
So
Is there research in this area in Bangladesh? I have not kept track
n- no, maybe I'm not
because
also
uh,
aware of.
yeah, Bangladesh now is really the world leader in textile. So this electronics integrated with textile would be very, very beneficial to future
Yes.
Bangladesh also. Okay, you are now the
Yeah,
leaders
there's
of
some
technology.
researchers who are doing this electronics field, but not
Yeah.
exactly this field. I don't know.
Okay.
So what the
Yeah, because
researcher.
I haven't heard of groups.
But
Some,
some of
yeah,
our research are doing well in electronics and
yeah.
other
Anyway, so
nanotechnology.
at least I'm motivating that you should, and this is not a very high capital intensive. Okay,
Yes,
even as in fact in India we are helping even small colleges develop this area because you don't
yes,
require
exactly.
very expensive equipment or material to start this lab
Yes.
and do some contribution.
Yeah, we're also trying to make some awareness so that the next generation student will join in basic research field.
Yeah,
So as
absolutely
you know that day by day, actually the research are reducing as
right,
everybody goes for other work, job, and business.
right,
So
right.
we are
Okay,
trying to do
you can keep
something.
it. You can open up the discussion to anything. Any other question?
Yes.
Not it need not be just what I spoke about.
Okay.
Yeah. Any other question?
So okay, I can show. Okay, one. This may be the last question.
Yeah.
The Kumar's theorem. What is the Kumar's? Could you explain it?
Okay.
Maybe you
No,
have
no.
already explained it.
There is no such theorem. Uh, this is really my calling it from Cromer's lecture. That is, um, uh, this is a new technology, okay, and hence this technology is not trying to replace a new technology. Will find new applications, okay, and hence one is not trying to say that this application is done by silicon. Now, can I replace it? Okay, so a new technology will survive if it can respond to new needs. Okay, that is what I call as the first Kramer theorem. The second one is that a technology succeeds not because you have been able to develop a good technology, but there are many other commercial value and everything else matters, and hence, and that is why every project that we do along with an industry. Okay, because as an academician I have no way of finding out whether a technology is going to succeed or not, but industry,
Yeah.
which is in the market, has a sense of what will sell. Okay, and that is why we don't do any project unless there is an industrial partner, because otherwise I'll be doing something for 10, 20 years and it has no application or nobody is going to take it. All right, and we are and I'm an applied physicist. Okay, and hence we would like the physics to be applied, and hence like many of you, many physicists, even 20 years ago I would not even worry about a patent. I was happy with my physics. But we saw that the new brand of physicists are both physicists in the lab, and they have to also do application oriented work. All right. Okay.
Okay, sir. Thank you. So this may be the last question.
Yeah.
So can we use this technology to improve the solar cells as a
Yes.
hybrid
Yeah.
new
Yeah,
renewable energy?
absolutely, absolutely. This is a huge area now. In India, we spend a lot of money in doing that. Okay, such that it can be for hybrid technologies. So inside, for example, OPV inside the room. Okay, so you can use that, and there is a huge amount of potential in renewable in using this technology. Absolutely, and we actually are
So,
funding a lot of projects in this area.
okay, sir. Thank you, sir. So, so I have one question. So some
Yeah.
of our students actually always asking me that what is the process if some of our students want to do their masters and PhD in any of your IITs. So is there any process, direct exam or
Yeah. We are now actually welcoming international students. Okay, a lot,
okay?
and we were not earlier so much. Let me tell you that. Okay, but
Mhm.
all this there is a criteria now for in the university rankings. Okay, where the international participation in students and faculty is an important criteria. And because of that, we are now welcoming lots of students. They have to just apply. I think our process is quite simple, and they would enjoy being here. And they have to just apply according to our. In fact, if they just apply, we'll also reply telling you when you can apply properly. Okay, and then have a communication.
Okay.
So we are
Okay.
encouraging both MTech and PhD students from abroad, and certainly from Bangladesh.
Okay. So thank you, sir, for your wonderful presentation and discussion session, sir. The main aim of our program is to motivate and encourage our students in this current of
Right.
pandemic situation. And I think uh, uh, some of our students and the viewers will definitely motivated by your lecture and exciting lecture. So thanks again for
Thank you.
giving us this opportunity to arrange such an important webinar. So bye for today, and hopefully in near future we'll arrange another webinar. And after the COVID, I'll definitely invite you to visit our beautiful country, and we'll
Okay.
arrange a face-to-face session. Bye
Absolutely.
for today.
Thank you. Thank you, Pretam.
Yeah,
Yeah.
bye, sir.
Good.
Bye, sir.
Bye.
You're welcome.